do I. So let's start. So I'll start pretty much from where Anthony left. Move away from the experimental side of it, take away the data and see that what is it that we can do with this biochar. Just some statistics for us. See are the agro residues that are burnt in the field. Rice standard about 40 to 50%. Wheat also, though wheat has an alternative use. We use wheat as an animal fodder. We are the biggest cattle holding capacity in the world. We have a very good dairy system in the country. But you could see that even wheat, rice and sugarcane, because these are the top 3 crop of the country, and all of them, because of the agro residue management, some part of it is burnt in the field itself. If you look at sector-wise emission in the country, energy contribute about 70% of the total emission that is happening comes from energy, followed by agriculture. And what we see industrial process, this is not, it is only the process side of it. The energy used in industry is already taken care in the energy sector. So please don't get confused at why am I putting industry below agriculture, right? It is the emission which is coming from the direct production of the industry. And then we have waste, and then we have land use change here that we can see. For land use change, our numbers are minus 31.3 because a lot of sequestration is happening in the land use sector in terms of increase in forestry and agroforestry practices that we are doing. So, and the commitment that the country has already made for becoming net zero. So you see, other sector, while they are becoming more and more emitting, land use and forestry somehow is contributing constructively. We are bringing in all those change here. And the emissions that are happening is also given to you just to set the context that this is the scale we are looking at how to mitigate it. So what happened right now, if you look at it, the rice and wheat straw are currently burnt. Majorly, the rice straw is burnt in the field itself to manage it. The problem is because once the harvesting is done, and for the next crop cycle, the field has to be clear. It's a huge amount of rice that we produce. And I'll talk about only 2 states today, which is Punjab and Haryana, because every November and December, when the harvesting is done, the capital of the country actually suffers. And maybe because the capital suffers, it becomes a national and international news, right? And yeah, so what is it that we can do about it? I'll just give you some numbers here. So what we are proposing here is that we have the crop residue. So we have the crop residue here, as you can see. We have the crop residue here. We are proposing a pyrolysis route. We are not proposing here in-field pyrolysis. We are not saying that do the pyrolysis in the field itself. The separate pathway that we are proposing. So we do the pyrolysis, we produce biochar, and we use a part of the biochar for coal replacement. Okay, which I think Sonal would not be very happy about it, but hold your thought, it's not the solid biochar, we are talking about something else here. And a part of the biochar will go, as in the agricultural field, like Sir said, belong to farmers, goes back to farmer for soil sequestration. Okay, so 2 pathways we are looking at it. What is it that we can do at a thermal power plant, which is coal-fired, and how we can mitigate and use it as a sequestration tool in the field itself. Okay, so this is the state as I talked about. We are looking at Punjab and Haryana. This is a 2 major state which is grows rice and wheat both in huge quantities, primarily rice. So this is our system boundary. We have taken it, what I am presenting here is for the financial year 2021 and 22. The data will be produced for these financial year only. This is our system boundary where we are using biochar for carbon sequestration in soil, and as you can see here, for input we have taken all the machinery. Those who do life cycle assessment, they know about it. But this is our system boundary. These are the inventories that we have created here. So straw collection, how it will be done. Then it is transported to the thermal power plant. So what we are proposing here is that we will collect the agro residue, take it to the thermal power plant. At the thermal power plant, again we have sets of machineries that are used there, treat it, all sorts of pyrolysis will happen. We will produce electricity out of it, primarily from the volatiles that are coming out of the biochar, or the biomass. And the solid biochar which is produced will be transported back and will be used in the field for soil application, right? And as you can see here, it involves lots of processes, all the red color boundaries are the processes here. So we have taken into consideration, as you can see here, straw collection, we have taken it on the nodes, maybe it will become. So we have taken nodes from where the collection will happen. The second node is at the thermal power plant. And the third node is again the district headquarters where the char will be transported back. More clear when I come to the next slide. The methodology that we have used for this estimation is ISO 1440, as you understand, primarily used for life cycle assessment. We have done it for scope 1. Some data we have used for scope 2 also, like for example, for electricity generation in the country, the Central Electricity Authority has given the emission factor. That means for 4 megawatt hour electricity that we produce, about 0.7 tons of CO2 is emitted. So that is a kind of, you will say that it's a scope 2 because we have used the real data that is available with us for the country, but where it is not available, we have used the scope 1, that is the global data that is available. We have used tier 1 and tier 2 data sets, and we have, all the calculation was done by the IPCC guideline, and it's developed in MATLAB, Simulink, and using the GABI data set. So what we see here is there is feed, all the fields are marked, then we transport it to the nearest power plant. And of the power plant, the green one, as you can see here, this is the result I'll be presenting to you too, where the biochar will be 100% of the biochar, that is a solid material, will be used for sequestration. It could be done both ways. The dotted line, as you can see here, these dotted line, you can either try partly used as a coal replacement in the power plant, 100% or partly, whatever it is, could be done. The model is capable of doing it. But today I'll be presenting from field to nearest power plant, goes back to the field. Whatever gas and liquids or condensable that are released will be used in the power plant itself as an alternative or additional fuel. If we were to come to that, we have done certain experiment and various feedstock, as you can see, rice straw and wheat straw, we have presented here what kind of ultimate analysis is there, like what kind of carbon, hydrogen, oxygen, proximate analysis and all. So that will pretty much fall in the same category of the biomass, the range that we provide. We have also done the TGA and the DTG profile of it, and like a typical TGA profile, we found that as we increase the heating rate, because heating rate is an important parameter, which was emphasized by Anthony as well in his previous talk, that you see a lot of change that happened here, right? And you see that the DTG curve, that peak moves really up very fast as we move to higher heating rates, right? So we did that primarily to see that what kind of char is produced, because here the idea is to produce high value char. And we see that for making char suitable for sequestration purposes, literature says that the peak deposition rate should fall between 6 to 8% per minute. And we found that 6 to 8% peak deposition rate actually comes at heating rate of about 10 degrees Celsius per minute. If we are using that heating rate, we get, that is an ideal process parameter for biochar production. So we identified that from our TG analysis. And this is the reactor, it's a PLC controlled reactor where we did the experiment, where we produced the biochar at different temperatures. There are some of the samples just to show you that we actually did the experiment and we have the data with us. And yes, the yield distribution, as you can see here, what kind of char yield we got. Here, I'm not presenting the case for sugarcane today, but this particular graph has the sugarcane, the blue line talks about the sugarcane, but let's focus on the black and the red one, which shows the kind of yield we get, biochar yield we get as the process temperature goes up. And as you can see here, that at lower temperature, it is pretty much anticipated, we get higher percentage of char yield as high as up to 40%. But when we move to 500, 550, 600, it goes down, and typically about 30-35% and 20% is the yield of biochar which is produced. Yes, this one, that was about the yield, and this here I'm just presenting the final data here because it includes extensive analysis of the biochar, which includes the SEM, the BEC, which is the surface morphology, the NMR study, the total organic, FTIR, XRD, and the light microscopy as well. So all the data has been put together, and we see that, again I'll request you to focus on the blue and the purple one and ignore the red one. So you see here that, for example, how you to read this data, that the char which is produced, the heating rate is 10 degrees Celsius for all of them. The char which is produced at 350 degrees Celsius, only about 40 to 45% of that char will remain if used for sequestration in the field for about 100 years. These are all probability. But the char which is produced at about 600 or 650 degrees Celsius, about, as you can see here, the yellow one, as you can see, more than 80% of the char will remain sequestrated in the field for 100 years. Okay? That means that as if the char is produced at higher temperatures, very evident from here, if the char is produced at higher temperatures, more will be its stability in the soil. It will stay for a longer time. It will remain locked for a longer time in the soil. Lower temperature, if we are making it, it will disintegrate and go back into the atmosphere in less than 100 years. Because IPCC and all, they primarily focus on 100-year timeline, that for how long we can hold it in 100 years is important to us. 100 years is important to us even when we are looking at the carbon credit business. That's why we see 100 plus. And this one, as you can see, the methodologies that we have used are the ones that are recommended in the European Biochar EBC guidelines, Biochar certification guidelines. Right. So what we concluded from these extensive experiment, was that ideally we should do the experiment between 500 to 650 degrees Celsius should be the pyrolysis temperature, having a heating rate of about 10 degrees Celsius per minute, and ideally the solid residence time should be 1 hour, because we also checked that different residence time, and the one which was 1 hour and more than 1 hour gave us very stable biochar. And of rice straw and wheat straw, both of them, which is produced at 650 degrees Celsius, 10 degree heating rate with solid residence time of 1 hour, we use nitrogen as the carrier gas, like Anthony used argon as the carrier gas, gave us the most stable biochar. So let's get back to that. Was all about the experimental part of how we identified at what process parameter the char should be made. And here we looked at the collection part of it. So we identified all the districts here, both in Punjab and Haryana. So these are the two states who are held responsible for the bad air quality of the National Capital Territory. So Punjab and Haryana, as you can see, all the districts are mapped here and the headquarters are mapped here. Now for ease of business kind of thing, like where should we collect the char? Where should it come? Not char, where should the agro residue should be collected, like field to field, right? So you have to put in some kind of an assumptions have to be put in place. So the assumption that we made here is that let's collect all the feed at a node, and the node is a district headquarters. So all the residues are weighed and are brought to the district headquarters through the road network, and from the district headquarters through the road network, it is taken to the nearest power plant. So if you look at here, it has all the district headquarters, thermal power plant, and the connecting road. Maps are put in place. As you can see that the triangles are the thermal power plants that are there. And we use the road network through the ArcGIS, as you can see, from the ArcGIS software, and we use the distance minimization function so that it takes the shortest route, surface route transport to reach the thermal power plant. And this one gives you the kind of agro residue that is generated in the state. So the red ones are primarily the outer one, the black ones, as you can see this one. This one tells about how much residue is produced, and the red dots are the ones which are actually burned in situ. What percentage of that residue is burned in the field itself, right? So all the data they're put into the model. And equipments, as you can see, as I told you, it's important when you do the life cycle analysis what kind of inventory we have created. So all the equipments are given here, what process it is used is mentioned here, what emission standard that we have used, because it is happening. As I told you, we are using tier 1 and tier 2, so the Euro standard and the Indian standard, which is the Bharat standard BS, and the Euro standard norms, both of them were considered. Local tariff were used, whatever is prevalent in the country, and we made predictions. So this is how we did it. We did the thermogravimetric analysis, the chemical analysis, ultimate everything, identified the suitability, used the conversion route, and yield and everything was predicted. So scenario 1, what I will be presenting you is that the business as usual. Like whatever I am proposing, if we don't do that, what kind of emissions will happen. And when I am proposing the pathway, the scenario 2, as you can see here, what kind of an emission reductions are possible or could be avoided. So very quickly I'll present it to you. So if you look here, what is written in the text is pretty much represented here in this figure as well. So rice straw, if we look at, this is the gross residue produced. This is in Punjab and this is in Haryana. And what you see is the in situ burning. So you can see rice straw is a major problem. Wheat also we do it, but then the scale of wheat is small. Two reasons why wheat burning is not an issue. One is because the scale is small. And second, unlike at the time when the rice straw is burnt, the wind is going toward the northern plain. So it brings back everything to the plains of the country, and therefore you see so much of hue and cry about it. Right? But this is, what I'm trying to say here is that rice straw burning, in scale it is also bigger, and that requires major management as well. This is the crop residue, and this is the kind of emissions that happen because of the burning of the rice straw. So we went into the field and we do all the measurement, and we saw that yes, there is CO2 emissions, there's a higher percentage of CO2 there. There is CO also. These small numbers projected here, as you can see, we have PM particles 2.5, 10, SOx, NOx, nitrous oxide, ammonia. There is methane, there is volatile matters, there is pure carbon, elemental carbon there is organic carbon, and then there is polyaromatic hydrocarbons. As all sorts of these pollutants were detected in the field itself. And the numbers are also there, it has been quantified here. And what is the impact of that in terms of global warming, in terms of CO2 equivalent is also represented here. So we see here what is the impact of CO2, it is maximum, it's GHG gas. But other NOx, for example, has a cooling effect, right? Therefore you see it as negative organic carbon for that matter as well. So the impact of the absolute number is projected to you, the kind of emission that is happening, and you're also seeing the impact of that on the climate. That is for crop burning. The same thing, that was the business as usual scenario 1. And what happened because of coal burning? Because when we do coal burning, again we get all sorts of emissions. There is CO2, CO, PM particles, SOx, NOx, and volatile carbon. And equivalence of that in terms of climate, right? So what is the footprint of these climates when it comes to heating of the atmosphere? What we did, I'm not presenting the model to you, it's a big model. What we see here that biochar potential is to sequestrate about 8.8 million tons of carbon. This potential is there after all the consideration that we have done. Discounting all the emissions that it is embodying in itself, right? So after discounting all this is the absolute sequestration that it is. So the net sequestration that it is doing is about 8.8 million tons. Yes, like you said that, like Anthony said in the morning that it is an energy-intensive process. Yes, it is an energy-intensive process, and you can see here that about 5.8 terawatt-hour of energy is embodied in this biochar itself. Because while you were making this biochar, it has embodied energy into it. So what kind of energy it has embodied into it, what kind of emission it has embodied into it, all those things are considered and are discounted from this 8.8 million tons. So after discount, we are getting this number of 8.8 million tons. And the volatiles that were released, since we are proposing them to be used as a source of energy in the power plants itself, also because in Punjab there are few power plants that actually works on gas, which are gas-fired power plants. So they have the arrangement available with them how to fire gas. So their equivalence is about 8.7 million tons of coal replacement. So the gas part of it itself can replace about 8.7 million, in terms of energy equivalence, can replace about 8.7 million tons of coal. Now what does that mean? This means that, again these are some numbers, but the takeaway message here is that if we can incorporate that together in terms of sequestration plus the coal replacement, can bring down the GHG emission happening from the electricity of the country by about 12 to 14%. So whatever emission we are doing right now from the energy sector, which is about 80% of the total emission that we are doing, we can actually bring it down by 12 to 14%. Simply by managing the residue which is coming from these two states only. Yeah. So this was all about the life cycle part of it, and very briefly to both of you, because I said we got the result in terms of how the biochar looks like in terms of reflectance. So if you look at it, this yellow part of it says these are, we call it as an inertinite, which is a very stable carbon form. It's a very, very stable form. It's like very stable coal. Like coal is known for being there the way it is for millions of years. So So this inertinite, as they say, don't ask me a question about it. These are the results that just came to me a week back. I have not done my analysis, but what I could see here, that wheat straw which is made at 550, wheat straw biochar which is made at 600, all same thing, 10 degree Celsius heating rate at different temperature. 96% of that, 95% of that, 92% of that, and more than 90% of that is actually inertinite carbon. That's a very stable, highly cyclic, bonded, stable form of carbon. And this is pretty much visible for all the yellow, if you look at the yellow size of it, right? So all the biochars, be it the rice straw which is here, right? And this is the wheat straw which is here. And this one is the rice husk. So you see that chars that are made at higher temperatures, they have very stable carbon. They have very stable carbon into it. And the claims are, don't give me those look, I'm getting some very dirty looks from many people here. But they are stable carbon, this is what is claimed. And we also found that yes, they are in terms of analysis that we do, all the analysis that has been recommended by the European Biochar certification as well, that these are stable carbon and they can lead to long-term sequestration. Thank you very much. With this, I come to an end. All of us come together.
Thank you very much, Professor. Now the presentation is open for the discussion.
Long live India and France friendship.